Very warm welcome from my side. My name is Alex from SimScale. I'm a product manager and I'm responsible mainly for our electronics and thermal management offering. And I want to talk today about EV powertrain optimization and most importantly about using the all-cloud software stack for it. We'll directly jump into it. So the agenda is a quick welcome and introduction. Then I will tell you a little bit about why the all-cloud software stack can empower engineers, and I will give you some case studies as examples, both the physics that we want to look at, but also some example workflows that show you how you can collaborate with your teammates around these projects. And then we will take a look at a live demo on the platform. We will have a quick summary, and in the end, there's a Q&A. SimScale, the company, was founded about 10 years ago. We have offices in Munich, Boston, and New York, but we have employees across the globe. That is also very important for the way how we do our live support for our customers. We will see this later on. And you can see we have a lot of users and simulation projects. Those are partly our customers, but those are also research projects, hobbyists, etc. This is not the first time we are at the virtual conference. Today we speak mostly about the platform and broad range of physics. If you're interested in more specific use cases, we've talked in October about an API-driven use case, so a liquid cooling channel, geometry optimization, and in the April session, we've shown how Rimac Automobili enables their engineers with SimScale, and they provided also this nice dummy battery pack where we showed exactly how the simulation setup can be done. If you're interested in one of these, they are still available on demand on the website. So let's get to it. Why empowering engineers? You know that simulation is already used for years in the industry and was used to build great products and participate in innovations, but it's still not used to the extent it would be valuable. And that's the big problem. There's various reasons for this, but the important point is with the arrival of the all-cloud software stack, there is no good reasons for this anymore. And I want to explain to you why that is the case. So with a cloud native tool, you only need essentially a standard web browser and an internet connection to get started. That means your employees can work from home. They can work while they are traveling. There is no painful setup with remote access, etc. It's really easy to get access. Additionally, all the physics are available on just one platform and all teams can get access. That means you don't have an ever and always firefighting expert team that has week-long simulation queues, and you don't have engineers and designers waiting for them. But essentially all can get access and simulate, but there's also no work in silo. So there's essentially the possibility to collaborate. There's the chance for the experts to support their colleagues. They can control the quality. They can provide quality standards and templates. And you can also make use of our simulation experts via these collaboration tools. The most common one is probably the scalability and flexibility. So that's a great advantage of using a cloud solution. There's basically no limit in regards to simultaneous usage of your team or simulations in parallel, but it also allows you to get started if you don't have now simulation jobs ready 24/7, as we can put together a tailored solution for your needs. And that means we can run this quite cost effectively. So as a summary, you can think of if you ever think that simulation results would right now be valuable for you to make an informed decision, maybe have an edge over competition. Essentially, there's no good reason to not go for it, and it's just a few clicks away. That brings us to the case studies that I want to show you today. I looked around a bit for inspiration and I found it with our hosts, so Charge TV, as they are speaking about so many different topics in the EV industry. So I took a look at the main topics that are listed also on the conference website. So that is motor design, manufacturing, that is battery systems and power electronics, and a few more topics that are really interesting and important. And I want to walk you essentially through a physical case for all of these. So like in this case, for the motor, a rotational vibration case, I want to show you a typical workflow that you could use with your team and colleagues. And I want to provide you with a quantitative result that you can use to make an informed decision. In the case of the battery systems, I want to show you an air-cooled battery module where we will look at the conjugate heat transfer and joule heating, so a thermal analysis of this pack, and we will derive a system pressure resistance curve. For the power electronics use case, I chose an EV inverter where we will also run a thermal analysis, and we will look at the liquid cooling pressure channel. So we will come up with 2 different design variants and compare them. And as a last but not least, we are really interested about your daily work and challenges in your organization. And we hope we can help you actually build better products and that your project is actually in the next one on SimScale. Great. That gets us to the live demo. I will quickly exit the presentation mode here. And as you can see, I now simply switch over in my tabs. You can see the URL on top. So I now entered my dashboard on SimScale. I'm here in a standard web browser. So this is Google Chrome, but any other web browser would work the same way. And you need obviously internet connection. I'm also running on a standard laptop, so you don't need any special hardware to get started. You can see here my dashboard, so all of my projects are listed here, my own projects. I also have a team space here. So that is essentially my team, the mechanical engineering group, and I have access to the folders and spaces in here. And in my case, you can also see here an admin section with manage teams. So I can actually manage the mechanical engineering group. I can add members, remove members, and I can also decide on what standard sharing would be present if you create now a project inside of this shared area. So no sharing within the team or within the organization. So you have a really close control on what you want to do with your team. Also, for example, prevent any of these projects to ever be shared to public. But you can obviously also use it to share it with your customers. So we directly want to get started after this. So I'll go into the mechanical engineering group again, and I will now look at a project that was created by my colleague John, and I will just open up this project in the workbench. So that's now the 3D environment where we can see the simulation model. In this case, there was a pressure drop analysis on the liquid cooling channel, but we can see there are more simulations listed here, where we are interested now in the frequency analysis of the rotor. So this model, we see again that this is John's project, it's private, and we don't want to do anything with this project except for extracting now data. So I cannot modify this is John's, but I can go through the setup. I can see that he set up here a centrifugal force as the vibration analysis or the resulting eigenmodes will be influenced by the rotation of the part itself. That was set up here, and you can see that John ran here a detailed parametric study for different RPM values. And for all of these simulation runs, we can take a look at his results. So for example, the eigenmodes, we can look at the eigenfrequencies, and we can take this data later on to create a Campbell diagram. We will see this in the summary later on. But we can, of course, also click on solution fields, so look at the real 3D data that was created here and take a look at how visually these eigenmodes actually look like. This for the 2000 Hertz eigenfrequency mode, or we can switch to the next one and take a look how this one looks like. So we can basically have a complete overview of what John did here, and that was the first workflow that I wanted to show you. We'll jump back to the dashboard. I will go back to mechanical engineering group, and we will open up now the battery pack, as this is now kind of our second workflow. So we'll enter this project again. And in this case, we want to take a look at John's project here. I already mentioned before that John ran a fan analysis study on this battery pack. So we'll take a look how he did this and which results he got from it. And we want to then get this further by essentially running a system resistance curve study. So first we'll take a look at John's project. You can see here again the setup, how it is listed, all of the materials, for example. In this case now, I potentially want to modify this project. So I need to request, in this case, edit mode from John if he's currently working on it. And you can see that John is shown up here. So what I will do is I'll quickly request edit mode, and John gets now in his user interface a pop-up window asking if he wants to allow this to me. So if we're lucky, in this case, I got the permissions to now edit this project. It quickly reloads, and now we can use it as if it would be our own project, and we can modify this project. For example, I could bring in a new material from the default library, or I could use the materials that are only available in my organization, where I can also add new materials, and I can modify all of the rest of the setup if I want to. So for example, in this case, we simulated the thermal behavior, but at the same time, we put in, for example, the electrical conditions. So we have here a current drain of 40 amps in a probably 1C scenario for this battery pack. Maybe we also want to take a look quickly inside how this model looks like. So if you hide the flow region, we see the different battery cells in here. And now in the simulation, we solve the electrical field. So for example, the current density that provides a thermal input, so a joule heat generation that is then solved with the flow field and alongside the heat transfer, so that we get an accurate representation of the thermal behavior of our system. And the flow behavior here is defined by our fan boundary condition. So you see here there's no single value, but instead there was a fan performance curve uploaded, so different flow rates and different expected pressure drops for this fan. And what we get out of the a simulation like this would be the exact operating point. So what will be the pressure drop in the system and the flow rate that this specific fan provides to us. We can again take a look at the results that John created here. For example, we can take a look at the different area averages. So we can click here on the pressure fields. Those are values now for the inlet and outlet, and we can see here the roughly 30 Pascal that we get as a pressure drop in here. We can take a look at post-processings that were saved, in this case, for example, a screenshot. So you can see the current density field that is the input for the thermal analysis as well, but can be also looked at if you, for example, want to optimize certain sections, SIN sections, where you have current spikes in the bus bars, for example. And we can now use this information by duplicating the simulation that John created. And what I want to do now is I don't want to run now a second fan, but instead I want to run a set of flow rates to derive the system resistance curve, to understand how our battery pack behaves for certain flow rates. So what I will do is I will change the fan boundary condition here to a velocity boundary condition with a fixed flow rate, volumetric flow. And instead of providing now one value and running just one simulation, I'll choose here a parametric value. So I can now type a number of flow rates here, or instead upload, for example, a CSV file, as I do here, all the flow rates that were provided also in the fan performance curve, and I click apply. Now I can see this updated to a parametric value, and later on the simulation will execute all of these different flow rates all at once. This is also what I will just do next. So I'll click here on start simulation. It starts now 11 simulation runs all in parallel that I can later on again access, all of them separately, but I can also look at the overview of all of these simulation runs. So in a second, this will start and show us the 11 simulation runs. And obviously the simulation time that we now require for these 11 runs are just the simulation time that we would need for just one simulation. So all of them got now started and will be now executed in the cloud. I did this beforehand so that we can also take a look at the results. So my experiment already finished. All of the runs have completed. That took me 80 minutes. All of them obviously ran in parallel. So roughly the time for each run was exactly these 80 minutes. I can now access these, or I can take a look at the comparison. So I'm accessing the result controls, and I want to take a look at the pressure field. I had on the outlet a 0 pressure value, and now I can look at the different pressure values for the inlet that represent essentially my pressure drop. So these values I can again extract, and we'll take a look later on in the summary what this means for our decision-making process. That was the second workflow that I wanted to show you. The third one, I will just briefly show you how I can do, for example, a design study on SimScale. So in this case, I will now copy John's project instead. So I want to make this my own project. Maybe I want to work with multiple iterations. I don't want to have this now in John's project, but I want to test it in my own copy. So now I have my own project of this. I have the setup of John, where he again simulated this beforehand. So I can take a look at the screenshot, for example. We see the liquid cooling channel of this inverter, and we assume maybe we want to test a potentially better version of it with a lower pressure drop or higher thermal cooling performance. And for that, I can bring in a new inverter model. So you can see here, and this is John's setup. I can hide here the flow region, and we see the different elements, turbulent elements in this liquid flow channel. I brought in now a second model. I can hide again here the flow region, and we see now the different liquid cooling channel in here. I can simply do so by importing a model from my computer in kind of all the standard formats, or I can bring it in from Onshape or, for example, from SolidWorks via plugin. And I can, of course, modify these models also in SimScale. So, for example, in this case, I added the flow region. What I now can do is I can duplicate the simulation that was done by John. And now I'll just select this second model. What will happen now is that all of the assignments that were done before, we can see here the different materials that were assigned. We again see the boundary conditions. Again, we have here an inverter model where we have a lot of electrical components, like we have the bus bars, the MOSFETs in this model. So we want to actually have the current field defined here again as well. And now the update is completed. The contacts were again created, and all of the assignments are still in here. So that is all I needed to do. As this was completely set up by John before, I can simply now click start and run this. Start the simulation. I get again a quick indication on what's the expected runtime and computing resources, and I click start. If I didn't know exactly what I should be doing at any point in time, I could have clicked here on the help and reached out to one of our support members and get a direct message. So you don't need to wait for any ticketing system or anything. You can directly get the help that you need. And in the end, we can again take a look at the result field. So here we see this in 3D. I hided most of the components. We just see essentially the MOSFETs at the bottom, and on top here the capacitors, and we see the liquid flow channel, and could, for example, inspect this and see that we have a little recirculation zone here that we could improve in the design process moving forward. That was all I wanted to show you on the platform. So I'll quickly jump back here to the presentation mode and summarize quickly what we've seen. So in the first workflow, I showed you how you can take a look at a project from your colleague and get all of the information that is provided there, derive, for example, in this case, a Campbell diagram. So all of the simulations that were done for different rotational speeds can be taken to derive these eigenmodes dependent on the RPM. And then we can also see here the RPM curve. And if there is now an intersection between the rotational speed and an eigenmode. We know here we have a critical speed, so that might induce now or start the eigenmode to really damage our product. So we need to make sure that the operating range does not lie around this point. In this case, that's probably the case. We also looked at a fan simulation where John's simulation got us the operating point for this specific fan. If this is not the flow rate that we require, we might be best off running a system resistance curve study so that we get the exact behavior of our battery module. And we could now, just put in different fan curves of different higher performant fans and see which flow rate would we actually get from these fans and what would be the best fit for our battery pack. And as a last workflow, I showed you how to copy a project, bring in a new version of the design, replace it, and then look at the different parts. And you can then see essentially what's the pressure drop here, what's the critical component temperatures, and where do you have the best behavior and what pump potentially you would need to take for such an application. Great. The last one I mentioned before, we would really love you to bring your challenge to SimScale, get your team involved, get us involved. So I hope your project will be the next one. You can simply get access by typing simscale.com or simulation.new in your browser or reaching out directly to us. And yeah, please remember, it's just a click away essentially to get your model started. That was it from my side. Thank you for your interest and your attention.